right. Good afternoon, everyone. And sorry I couldn't be there in person. Hope everyone is staying well hydrated in this summer heat wave. I, for one, am really struggling here in London, so hopefully Nancy's a little bit more bearable at this time. Today, I'm just going to provide you with a bit of an overview of some of the work that we've been doing to bring Gemini into the physical world. As Serena mentioned, I work at Google DeepMind. I'm actually a research engineer. I started off as a program manager in the team, and I've been working on Gemini Robotics for the last 3 and a bit years. So hopefully I'll be able to share a little bit of the track record of what we've been doing. I don't know if questions are during the presentation. If so, just please speak up and let me know. I will provide references to the main tech reports that most of the slides are based on. There is some material or some things I probably can't answer, unfortunately, but hopefully there's more technical details in the reports that can be useful if needed. So just sort of zooming out slightly, big picture, what do we do here at Google DeepMind? So our mission is to build AI responsibly to benefit humanity. And taking that to within the robotics domain, our goal is to build embodied AI responsibly to benefit humanity in the physical world. So very much thinking about the interplay between AGI and the physical world and how those two things can be brought together in a safe and a responsible manner as well. And why do we care about this? I mean, for many of us, this promise of intelligent general purpose robots still eludes us, I think it's fair to say. We want robots that can interact in the daily spaces that we occupy. We want them to be general enough to deal with all the scenarios and situations that we encounter on a daily basis. We want them to be able to operate safely and maybe even help us in domains and situations where perhaps there's danger involved or things that we want to be able to have in a more scalable solution. So this is the promise that I think we're all striving for. I don't think we're quite there yet. So the question is, what are some of the ingredients that we're looking for in order to try and push towards this? That is a very long list, of course. I'm highlighting maybe 3 of the core ingredients that we think might be useful as we embark on this journey. So, one is, where do robots develop, gain, and kind of execute these competence skills that are needed, especially those that are highly dexterous and require whole body manipulation to operate in the human spaces that we occupy? How do these models and robots reason and interact with us and be able to adapt to all of the scenarios and changes that we as humans and animals seem to be able to respond to in a very natural way? And ultimately, how do they generalize? How do they move beyond simply the tasks, instructions, and environments that they are fed in their training data, but are able to actually extrapolate beyond that to really operate in the general form that we are looking for? Maybe just to provide a bit of a sort of a summary of kind of where we are now in some of those domains, at least the way I see it. I think when it comes to developing these kinds of competent skills, in many ways, we're kind of at a stage where we can kind of learn any skill that we can teleoperate. I mean, that's a broad statement, but I don't think that was true probably even 2 or 3 years ago. I think as the ergonomics of teleoperation for many devices has really improved over time, and as we see these models, such as diffusion models, being able to kind of capture these multimodal distributions, I think more or less, if we can teleoperate it, we can probably learn it. And some of the examples from the Aloha doing very complex things seem to be on that pathway there. And of course, there's still an open question of, well, what if we can't teleoperate these devices? Where do we go from there? And so perhaps using reinforcement learning, simulation, being able to have devices that are controlled not directly to teleoperation could be one way to generate the necessary skills that we want to be able to learn from. When it comes to reasoning and interacting with, being able to leverage large language models to help us with reasoning, planning, holding these situated conversations. Here's an example from our work on SEICAN from a few years ago. Kind of give us a sense of how we can absorb this knowledge that exists from these large language models to be able to guide and shape robot policies, to be able to have executions of longer horizon tasks, be able to interact in more natural scenarios. And in many ways, this sort of culminated in our work with RT2, where we, I think, coined the term the vision language action model. I think this was one of the first examples where we took a pre-trained VLM that had been trained on internet scale vision language data and was able to adapt it to be able to output and actually control a robot in the physical world. This was interesting because it started to open up these sort of new forms of generalization that I don't think many of us had seen before, being able to do what's obviously now considered quite toyish, but still at the time I think was quite interesting. Things like moving the Coke can to tailor Swift, which was definitely not something that we collected data on at the time, as well as doing basic arithmetic. So being able to kind of fuse together or bridge together robot control with some form of reasoning to be able to complete some of these more outlandish tasks over here. RT2, of course, is by this point a fairly old model. At this point, we were only controlling a single robot. I think the maximum frequency we could operate at was kind of 2 hertz, but I think this was kind of a glimpse into where we might be able to take these more general purpose knowledge, these general purpose models from. And so one of the parts that I think we're exploring more closely at the moment is kind of approaching this from 2 angles. So there's one open question of how do you make frontier models feel more embodied? How do they have greater awareness of the physical world, of spatial awareness, of the ability to kind of reason about time and space in a way that is much more embodied and situated in nature? And then on the other hand, how do we make these kind of skilled robot models more general, to be able to kind of complete actions, tasks that are far broader than just the strict skills that they're trained on? And I think the fusion of those things is an area that we're actively exploring right now. And much of this kind of exploration happens within our Gemini Robotics work effort over here. Gemini Robotics is actually a series of models at the moment. There are 3 kind of model families that we have been iterating on. We have obviously the VLA, the Gemini Robotics kind of flagship model, which is primarily cloud hosted. We have an on-device optimized version of that can also be explored with various trusted, tested partners, and has also been optimized for not only local deployment, but fast adaptation as well to new skills and situations where maybe more data scarce. And then I believe there will be a workshop this afternoon to talk about this in more detail, but also the Gemini Robotics embodied reasoning model, which is a VLM that has been fine-tuned to be able to absorb and deal with more reasoning in the physical world as well. And I'll provide a little bit of an overview. So over the last sort of year or so, I think the team has had a number of sort of interesting things that we've been talking about. This is just sort of a bit of a timeline of that. Today, I'll primarily focus on Gemini Robotics 1.0, the paper that we released in March, and then Gemini Robotics 1.5, what was out in September. And as I mentioned, the workshop on the ER will kind of dive a bit more deeper into that aspect. So I'll just start with kind of Gemini Robotics 1.0. I'll approach this more chronologically more than anything else. What did we do here? So with GR 1.0, we started from a Gemini model, in this case, the 2.0 series of models from Gemini. And we started from those, and then we started to train it specifically on robotics domain knowledge and 2 forms of data. We had embodied reasoning data, which was primarily around spatial reasoning, about being able to identify points, bounding boxes, other things that can help induce some sense of a relationship between objects and geometries. And then, of course, robot action data, and being able to have a fairly large, diverse set of robot behaviors that we could train upon. And from this, we were able to develop kind of this advanced reasoning for robotics applications. So some of the use cases that the ER model at the time was capable of was object detection in 3D spaces, 2D object detection, pointing, point and angle predictions as well. And then the action model, actually, we started to have this very general and instructable VLA model, primarily on the Aloha robot platform at the time, that was able to accomplish up to, I think, 50 or 60 tasks at the time from a very, very large, diverse set of robot data that we'd collected over a series of 12 months on our fleet. And then what we were able to do is take that particular checkpoint and start to see whether we could adapt it to new situations and new scenarios as well. So we started to look at more long horizon dexterous tasks. We wanted to look at new embodiments as well as other forms of advanced reasoning. And so this model had these different aspects that we were able to pull together in this particular instance here. Just as a sort of a quick overview of the kind of the deployment of the VLA model in particular, obviously, it consumes a multimodal prompt, given a series of images, some proprioception values from the robot. It's language instructed. So what action should the robot take to complete some task? The model at the time was a hybrid deployment. We had a cloud backbone that was obviously deployed remotely, and then we had a local action model. At this point, it was a diffusion model that was then running locally on the robot that we were targeting. We output chunks, so not single actions. These were now predicting chunks. And by doing this, we were able to achieve an effective frequency of 50 hertz, which is what our Aloha platforms were operating at the time. So from RT2, where we were primarily operating at 2 hertz for our Meta robot platforms, which were primarily static, we were able to start to move towards this more dynamic regime of having more reactive control, even with this larger model in size. And there were kind of 4 key things that started to emerge as primary capabilities from the release that we had at that point in time. So there was a lot more generalization than we had seen previously. Even with this remote structure, we were able to still have a fairly interactive and reactive model that could respond to changes in the scenario quite effectively. We were able to move far beyond pick and place tasks to far more diverse settings. And it was also something that could then be adapted and molded towards new tasks and new embodiments as well. So when it came to generalization, what we were able to see, and I'll probably have to skip through some of these slides just I think in the interest of time. When we benchmarked the Gemini Robotics model at the time, comparing it to what was the previous best, I believe at the time, Pi Zero was their state-of-the-art VLA model on the scene. We were able to see that we were able to find some levels of generalization that move far beyond that particular setting. So we, in particular, explored visual generalization, so being able to adapt to new scenes, layouts, scenarios that visually perturb what we had collected at training time. We were able to instruct the model in different ways, be it new languages, be it with typos, be it with sort of more reasoning-oriented task instructions. And then action generalization, being able to complete similar tasks, but from very different starting configurations, different object instances than what were available in the data as well. So these were some of the angles that we wanted to explore in a bit more detail. I'll play a quick video. I'm not sure if the audio is working.
Help me get organized. Let's start by putting the pen with the other pencils.
Okay, I will move the pen with the other pencils.
I won't go through all the videos. I will share the slides afterwards so people can do it. Just to call out, so that particular scene that we were testing on, that was an unseen scene in the sense of those objects had never been used in that specific configuration. Many of those object instances were not even used there, and the instruction of putting the pencils with the other pencils required some form of understanding of, what is a pencil, what are other pencils, and how do I execute the set of actions to make that instruction, again, which is not something that we had explicitly collected data for at the time. The other aspect that we were interested in, and especially because now we were dealing with this sort of more remote cloud-based backbone, which was much larger than we would ever be able to deploy locally, and of course the inference time challenges that come with that. How do we still get fast, reactive, responsive motions from the robots that we're dealing with as well? And so some examples of that over here.
Can you put the bananas in the clear container?
I think you get most of the point. So, even disturbing the scene midway through execution, even with this sort of hybrid architecture that we were dealing with, we were still able to achieve fairly reactive, responsive, smooth motions, even with this setup. And again, thinking back to our experience with RT2, where we were operating at a 2 hertz frequency, those kinds of reactivity, sort of responses was not something that we had seen before. And then, of course, being able to move beyond some of the more kind of static pick and place tasks into more complex and dynamic, or more dexterous tasks as well. Some examples of this, which I found very interesting, were being able to fold some origami, which and again, I'll take a pause. So many of those tasks are actually sort of up to 1 or 2 minutes long in duration as well. So we're able to see whether or not more complex, long horizon dexterous tasks could also be learned by the model at the same time. And benchmarking our numbers across this is just a selection of 20 from the available training set. We did see fairly strong performance across the board compared to our baselines against having the equivalent Pi0 model, as well as kind of multitask diffusion models at the time, which we had done in our Aloha Unleashed paper, which came before that, which was one of the state of the arts for dexterity research. And then finally, adaptability. So most of the results I've just shown you were primarily based on the Aloha robot platform from a fixed checkpoint. What we also wanted to explore is, could that be a starting point, a suitable adaptable foundation that we could then start to shape into new directions and new changes? One is being able to move towards doing more long horizon tasks. I'll skip the video over here. And here again, we're doing a number of things which take far longer. So scooping nuts out of containers, packing a lunchbox, playing a series of cards, and again showing very strong performance. In many cases, we're able to adapt some of these to get reasonable performance from just 100 episodes of training data as well. So fairly data efficient for some of these tasks. Some of them required a bit longer given the complexity and the nature of it. But also we were able to take that same starting checkpoint, which had only seen Aloha data at that point, so it was only kind of an Aloha specific model, but also then start to adapt it to very new form factors and new embodiments. So we were able to take that model and post-train it towards the Aptronic Apollo 1 upper body humanoid platform, as well as a bi-arm Franca robot that we had in our lab as well. And so by doing this, that same model was now adapted to be able to control the Aloha robot. Primarily, we were controlling the upper body and the hands at the time to be able to complete a range of tasks, as you see over here. And then also for the bi-arm Franca, maybe some more kind of dexterous complex tasks, such as the NIST belt assembly, plug insertion, hanging the tape in a very messy situation that had never really been seen before in the training examples as well. I also mentioned that as part of this, we also looked into seeing whether or not we could enable Gemini itself to perceive and reason about the physical world. And so as part of the training where we were using this more embodied reasoning style of data, we were able to introduce new capabilities into Gemini, such as object detection, pointing, so identifying very specific points in coordinate space, multi-view correspondence, and also 3D object detection as well. One of the interesting use cases that you can imagine from that is if you expose some of those capabilities as tools and use code as sort of an interface between your robot controller and the ER model, you might be able to use that to actually have very interesting kind of control problems. Again, you're not using maybe a trained VLA at this point, but you can then orchestrate this sort of behavior here without needing to retrain any VLAs from scratch. And we also found it was interesting to do some sort of like in-context learning with that model, where we're able to kind of feed the model a series of or rather use the ER model to identify key points in previous trajectories, provide that as context to the model with the end effector positions, and allow it to predict new Cartesian trajectories that we could then use on the controller here. So being able to control a robot without actually having to use the VLA model was another aspect that we had. So that was kind of the work that we had done for GR 1.5, so of 1.0. So primarily, this was a model that had primarily been trained on a single embodiment, the Aloha, and then being able to adapt it to new scenarios, either with new robots or new embodiments. We then looked to take this a little bit further with GR 1.5. And so GR 1.5 was actually a far more, I think, general model relative to 1.0. It was natively multi-embodiment, was able to show interesting signs of being able to transfer tasks and motions that were collected exclusively on one robot and play it out on another robot as well. And we also introduced the ability at test time or at inference time for the robot to kind of think before it outputted relative actions as well. When we did this, we actually evaluated this particular checkpoint across 3 embodiments, across 200 tasks, and this was all using a single model and a single checkpoint, without any explicit action space alignment between the different embodiments as well. What we found here was, relative to the work that we had done previously, this was a far more capable model, both at in-distribution tasks, but also on those axes of generalization that I mentioned earlier. And primarily, I think this was one of the first examples of a natively multi-embodiment model. So the same checkpoint controlling the Aloha robot, which was kind of 14 degrees of freedom at the time, the Apollo robot, which was 32, and the bi-arm Franca, which was 16. And so without any explicit alignment of the the action spaces between these robots and operating at different frequencies, the single model was able to absorb and be able to kind of control all of them. And I think what was interesting about this is that we started to see some signs where data collected exclusively on one robot could then be played out zero shot, so collecting no additional data on the other platforms as well. And so here are some examples of some tasks that were collected exclusively on the biarm Franca, this was the first one on the left-hand side. And they were being played out one-to-one on the Aloha platform. So we tried to recreate the scene as best as we could. But this was without new Aloha training data for these given tasks. So these were kind of just zero-shot transfer time. So this is a tape hanging or an unhanging task. One that I found quite interesting is this this task to kind of remove the computer cable from the slot over here. And in particular, what was interesting is that the model, when it was being played out on the Aloha platform, not only did it kind of execute the behavior, it tried to mimic the same strategy that the data collected on the Franca robots had been doing. So in particular, using one of its arms to help kind of provide more visual representation of the space where it would sort of point at it. The Aloha platform was also trying to kind of recreate that same strategy as well. I think there's suggesting maybe there was some ability for the model to understand the way in which motions existed on one platform, even though they are represented in a different action space. What's the equivalent mapping between those things, and kind of trying to interpolate and extrapolate beyond that. Here are a few more examples. A task where you're having to kind of lift this pair organizer, which again we didn't have on the Franca robot. It was able to try and execute that there. Of course, a bit more messily in many ways, and not necessarily as proficient as the source robot, but still able to complete that task to kind of a non-zero success rate. And in addition, also sort of opening this chest of drawers, which again we didn't explicitly collect for. And we also saw some of this transfer as well from the Aloha platform to the upper body. So I can definitely see how having two biarm platforms with grippers make it easier to transfer some of those skills. But here also being able to do this on a very different embodiment with a very different end effector space, I think that was also quite interesting. So here being able to kind of clean the pair with a washcloth as a separate task that we didn't have data for on the human. And sorry, this slide is probably very small for those of you looking at the screen. But I think we also started to see what are the benefits of this multi-embodiment training. And so the light orange bars in the chart here are single embodiment training runs from the same underlying architecture. The darker orange ones are multi-embodiment, so being able to use all of the different data sets from across embodiments. And again, in general, we did see some gains from being able to train in this multi-embodiment setting over here. This, I think, primarily benefited the biarm Franca and the upper body humanoid platform, primarily because the scale and the volume of the data that we had for those platforms was far less than what we had for the Aloha platform. The Aloha platform, you can see that in some cases, actually, the single embodiment is more or less in line with the multi-embodiment. So potentially, the gains were more prominent on those platforms in which we had slightly less data. And then the final thing that we looked at is by introducing some techniques that kind of were explicitly designed to induce so-called motion transfer between the embodiments, we were able to take that a step further. So being able to have not only the gains from training in this multi-embodiment regime, but also having some of these abilities for the model to, as best as possible, transfer some of those sort of skill knowledge between the different platforms over here, again, provided us with a little bit of a boost. One of the other features that we introduced in this particular model was the ability to kind of think before acting. So, typically in a VLA, you consume your inputs and you predict actions straight away. What we looked at here is whether or not at test time, the model could actually first predict, if necessary, the next sort of step of the task instruction that it's aiming to do, as well as potentially, if necessary, the kind of a low-level description of the motion trajectory that it might need to do. So moving the gripper. Again, probably the text is very small here. Apologies. I'll definitely be sharing the slides so you can kind of see it in more detail. But this provided a little bit more like interpretability, I guess. We were able to at least understand, roughly speaking, what are the types of things that the model thinks it needs to do in order to complete the task at hand. It unlocked the ability to complete multi-step tasks, which maybe were a bit more challenging to do kind of end-to-end without this sort of intermediate reasoning. and also allowed for some form of error recovery. So at times where the VLA might have started on an action trajectory that was incomplete or would have kind of led it to the wrong outcome, the ability to kind of recalibrate itself through this was somewhat interesting. And
laundry, please.
Sure, I can help with that.
Put whites in white bins and the darks in the dark bin. Beautiful, okay. And then I can now switch this up on it. Sorry, Apollo. And it knows that I have done that and it will react. So this model is able to think while it acts. And I can actually read its thoughts as it's doing the task here. So I can see right now it wants to put the dark blue plants in the black bin, which is great. So you can see the whole flow of its thoughts here. And it's
there you can probably see the rest of the action. So in addition to the VLA model, which I brought up, we also continue to push the frontier of embodied reasoning as part of the ER model that we had. So here we were able to see whether or not we could achieve strong performance and indeed across a number of benchmarks there. And here we were able to actually introduce some new capabilities such as kind of state estimation and object detection combined, segmentation masks as well, being able to kind of extend the pointing capabilities, as well as trajectory predictions for given tasks, and also task and progress estimation. So as a given task is complete, the model is able to predict how close was it to actually being successful or being done. And this maybe was sort of useful for us to be able to use this model as a planning layer for tool and task execution as well. Similar, I guess, kind of to the thinking at action time I mentioned, given the gains that we've seen for kind of test time reasoning in other domains such as code and other complex reasoning tasks, we also found that if the ER model was able to have a more extensive token budget, could it start to kind of reason about the capabilities that it was looking to achieve and then lead to more sophisticated outcomes? This is just a couple of examples where, in order to read the gauge, the middle column here are some of the intermediate thoughts that the model was first outputting before it eventually provided a response over here. And I think this matches some of the experience that we might be seeing in other domains such as coding and other more language and reasoning-based tasks here. And what we saw over here is that as you increase the token budget available, so the number of kind of tokens available to think before you have to provide a response, that ER model, when we trained it in this way, was able to kind of scale a lot better with its predictions compared to the baseline, which was the 2.5 flash model, which is what the ER model was based on over here. So we were able to kind of induce more complex spatial tasks if you kind of wanted to tune the thought token budget that you allocated at test time. So if we kind of put these two systems together, where we have the embodied reasoning model that now also has the ability to extend tool use, and use code, as also use reasoning at test time, we're able to kind of, I guess, put together a sort of an agentic system of sorts. So we have our ER model that natively is able to ingest speech, text, images, which can come from the robot sensors. It's able to use inference time reasoning as and when it needs to. It has access to external tools such as Google Search, as well as code execution. And then also, if it needed to, it could then execute function calling to be able to trigger the VLA model and condition it based on certain language instructions to be able to complete a series of tasks that it wanted to achieve as well. And the VLA, of course, continues to ingest proprioception, images, and any sort of language instructions to be able to control the three robots that we have over there. Here's, I guess, a quick example of that.
Hi, Aloha. Can you use my location and sort the objects into the correct compost, recycling, and trash bins?
To perform the sorting task based on San Francisco waste guidelines, I will use the green bin for compost, the blue bin for recycling, and the black bin for trash.
Here we have on our agentic layers, both control the robot and have access to the internet. To sort the trash, they had to look up the rules and look at the objects on the table, think about where each object should go, matching the rules that it had looked up.
And in this case, if we were to test that across a series of more challenging tasks as well, we able to see that with that agentic movement, we might have been able to kind of achieve things that even the sort of the thinking multi-step planning process couldn't do, because you have now access to memory, you have access to external tools such as searching that can allow for more complex behaviors to emerge as well. I actually rushed through quite a lot of the slides because I was conscious of time, because I wanted to make sure there was enough time for questions. So I skipped some of the videos and some of the details of the tutorial, but I wanted to make sure there was enough time for questions, reflections, or anything else that I can dive into in more detail from you all.
So thank you for your talk. Actually, I will start. I have many questions. I have a row of questions. So in the VLA that you showed, the big VLA, is it like a monolithic VLA where the fact that you can do many tasks is due to the training data set? So the training data set has a variety of tasks, and so the VLA learns to deal with these tasks? Or it is like inside structure with a combination of mini VLAs that are like specific to a skills, and then there is a system to merge the activities?
Yeah, good question. So it's actually the former. It's a monolithic VLA. So at this point, it's a single VLA backbone trained on the full multi-embodiment data mixture. So that's from across all the different platforms that we had tested. The components are similar to what I showed in the previous slide, where we have the VLA backbone, which is the primary, and then we have a diffusion head as well that is sort of conditioned based on the VLA the backbone outputs. That diffusion component is also multi-embodiment and monolithic in nature, and is able to account for the different kind of action spaces and representations of the different embodiments as well. So it's kind of a single model, and even when we did the evaluation from it, all of that was run from a single checkpoint. So we didn't kind of post-train it for one embodiment versus another for the different evaluation that we run. We ran it all from the single monolithic checkpoint.
So in the output is like in the joint space of the robots, or the Cartesian coordinate or 60 coordinates of the end effectors?
It's in joint space.
In how do you, how can you generate if you have very different embodiments? Because in the, let's say, bimanual setup, I mean, you don't have a lot of joints, you have a simple gripper, but if you generate full Apollo, you have a lot of degrees of freedom, a lot of variability. So this means that the output is, you know, adaptive.
Sorry, I missed the last part. Sorry.
So how is the output? Is it fixed? Because
I think I'll have to refer to the technical report for you to see more detail. But it's a diffusion component, or the diffusion model is also able to account for the different dimensional shape. I guess we have the full action space of the maximum robot that we want to output for, and then we're able to mask selectively for other action spaces. But it's all one diffusion head, as it were.
I don't know, because I don't know if there are other questions. I can keep going with the thousands of questions. Because if it's monolithic, so it's very big, I imagine, the model.
We don't have the total parameter count here, but the starting point of the backbone was the Gemini 2.5 flash model. So that definitely doesn't run locally. That's quite a large model, which is why it has to be cloud hosted. And then we have the local action decoder that we can deploy. But that was actually also cloud-based as well. So the full system now that we run today is fully deployed from the cloud, and we're still able to match the control frequencies that we want using action chunks as the prediction target.
So when you train, sorry, I keep going until I see raised hands. So when you train, do you have a so you give the training data set with everything that you record, or you pre-select intelligently the data for the training, like you do some quality, I don't know, measure or some kind?
That's a great question. I would say in general we have some quality rubrics that we sort of that we look at before we would use data for training. So very obvious bad trajectories or things which actually don't complete the task. We definitely try and pre-filter them such that the underlying data that we have is as diverse but as quality as possible there. I would say that a lot of the time it's just more data seems to work well. I think there's definitely from my perspective a question of like, are we over collecting data on certain tasks? I think having a better estimate of the kind of information density in a given data set, therefore to kind of more intelligently determine how much of that data is truly needed to be able to learn a new set of skills or to be able to achieve a certain amount of performance, or to be able to kind of maximize the information that's condensed within it? I think that's a bit of an open question. So for now, I think we've been able to see that as we scale up our data, we tend to be able to scale up the performance and the generalization capabilities as well.
Any questions? Another one I have. I keep asking questions. So because of the way you handle different embodiments, so I can imagine very easily that you have bimanual setup 1, bimanual setup 2, so this is very easy to transfer. But if you have bimanual setup, or like a Franca or 2 Franca, and then you have transfer to Apollo, how do you I mean, it's not clear for me, how do you transfer in this case? Because like imagine the Apollo has to walk, so the Franca doesn't walk. So
the Apollo, so the version that we showed over here was actually just controlling the upper body. So at this point, for that particular set of tasks, the bottom was fixed. But I guess you're still controlling a very different end effector space, right? So not only is the joints and the waist was also being controlled, but also the fact that you're controlling hands rather than grippers changes a little bit of the action space that you're having to deal with as well. So yeah, it was definitely very surprising to see that some of those tasks which were completely collected on bimanual platforms, as you say, you can probably more easily imagine bimanual to bimanual transfer occurring. I think being able to see that on a very different form factor. Also remember, very different cameras as well. So on the Apollo, we only have 3 cameras without any scene cameras. It's primarily the wrist and 2 in the eyes, whereas on the Aloha and the Biarm Franca, you have actually more cameras for the scene itself. So yeah, some of those transfers were quite interesting to see. I think the question of like how that emerges, I think some of it, I can't share all of the details of it, but a huge part of it is having such a diverse multi-embodiment training objective to start with, and having, I guess, the actions being in joint space rather than fixing it to anything more specific. We did think about Cartesian and whether or not that would induce a bit more transfer, but then we also thought that over time Cartesian might break down if you want to control hands in a more dexterous and complete way. So yeah, it's definitely a bit more of a surprise to be able to see that level of transfer between those 2 embodiments in particular.
So did you observe some generalization to new you didn't have in the data set of training?
In this, yes, as well. So we were able to see, completion of novel tasks that we definitely didn't collect data for. Some of them will be in the slides that I can share with you afterwards as well. But in many cases, being able to cope with new objects, new tasks, new scenes, we changed the backgrounds, changed the tables. So definitely, so those forms of generalization were much more apparent than we had seen in previous models.
Not like in the task, more on the embodiment. Like for example, imagine you have like a bimanual setup with I don't know, 3 or 4 degrees of freedom in the torso, and then 6 to 8 degrees of freedom in the arms. And so the kinematics of the bimanual setup changes a lot, or maybe it's less joints. So did you see some? I don't know if it was done or not. If you saw some generalization, like the ability.
This was a sort of one of the slides. I think I have a couple more that I can add before I share the slide. But I guess this is one example of a task which existed solely, was only collected on the Aloha platform, which is cleaning a pear cleaning that sort of organizer that's shaped like a pear with a cloth. And that was something that was attempted by the Apollo humanoid platform. We also had some examples of opening and closing a wardrobe, which we collected on the Aloha platform. And again, the Apollo was able to attempt that same task as well, even though it didn't exist in its training data.
Oh, and I saw in the video of Apollo that it also changes the head. So it's also controlling the angle of the camera.
Yes, it does have to kind of control the neck joints as well. So there is a bit of active vision, I guess, that it has to contend with over time.
And this is automatically done by the VLA, or it is a consequence of the teleoperation data?
It's, I guess, as we teleoperate the data, we do have the ability for the operators to control all of the joints that eventually we control with the VLA, but it's not done via, there's no separate controller for the torso versus the neck versus the arms and the end effector. All of that is at inference time, all handled by the VLA natively.
And so the Apollo, you teleoperated the robot with the like VR setup or with the Aloha setup?
We tried a few different versions of it. I think in general, teleoperation of humanoids is a very active space. I think for these ones, VR was one of the primary ways that we achieved it. But I think especially as you move towards more whole body based control tasks, there might be some limitations in those schemes. So I think, yeah, the ergonomics of teleoperation for humanoids, I think, is one of definitely the open questions to be able to scale up the amount of data that we can collect on those platforms in the same way that we can now do with Aloha-style Jello-based teleoperation devices for bimanual setups.
So you also trained with human data, like pure human data, human videos, or just data with robots? Sorry, I'm asking a question, but...
Yeah, no, this is just robot action data.
Only robot action data, so there is no human data, like, because, you know, some people are doing a lot of training from human data or also from egocentric video just with the hands. And then, I mean, if you put those inside, maybe...
For this particular work that I'm talking about,
No.
no, we don't have human data at this point in time. I think it's a very, as you say, it's a very interesting and a very desirable source of data. I think eventually the question of, can we continue to scale robot collection, especially for more complex embodiments, is definitely an open one. So the dream of being able to learn from human videos is I think, a very appealing one, and something that I think we're all interested in seeing how best to exploit it. But in this particular case, this was just robot action data.
I thank you, because there is the question, like people say you have to augment the data also. Ah, yes. Do you augment the data with simulated data or just take real data?
This is primarily real data.
Important to know. Yes, we have questions, finally.
Hi, thank you for the talking. My question is related also what he asked before, Serena. You said that for the data set you collect only real data. So how far we are to train a VLA also with the synthetic data, like in simulation, coming from simulator or something like that?
I would say it's a very active field of research at the moment, right? I think we're all familiar with the challenges of sim to real transfer in some cases. Maybe that is getting better and better as our simulators also are getting better at simulating the real world. In this particular work, this was all with the collection, but I think from my perspective, absolutely, I think there's probably a ceiling on how far you can push robot collection on its own. And so, identifying new sources of data, be that synthetic or from simulation, to Serena's point of being able to use human videos, either labeled or unlabeled, I think those are very active areas of investigation right now. And then especially as people are thinking more about the use of other backbones for robot models. So World Action Foundation models also provide an interesting pathway, and how do we think about data collection in those regimes is, I think, a very active field of research. So I think, yeah, there probably will be a threshold of what you can operationalize when it comes to real robot collection, and especially the diversity of what you can collect for. So being able to generate other sources of meaningful data, I think, will be very important.
Okay, thank you.
We have one more question.
I wanted to ask some, thank you for the presentation, first of all. I wanted to ask about some insights about failure cases of these models, because they seem so amazing. And, I mean, they are, and if they have these capabilities also on multi-embodiment. Yes, some things about the failures, because just to understand the gap between the research and also the industry, this is a field that goes really fast, so I don't know, maybe in a couple of weeks we will have these models also in the industry, but just some insights on this.
No, I think that's a great question. I think if things had been, otherwise I would have titled my presentation "Robotics is Solved," and clearly it's not, because I think there's definitely like a long way to go. So I think some of the things I think are still important, at least in my mind. I think the big question that, at least personally, I think is important is that what seems to be trade-off between generalization and mastery or competency in a given skill set. And you brought up industrial challenges. In some cases, you might want to sacrifice or need to sacrifice generalization in order to achieve some level of mastery. At least that's the paradigm that we've sort of been operating in for quite a while. But for me, the question is, whether or not there's a relationship between the more general you are able to be, and the greater awareness you have of a broad range of motions and tasks. Is that a necessary prerequisite to be able to really excel and achieve mastery in a more general sense as well? So, for me, the failure points here are, of course, these are lab settings. I unfortunately did not show you videos of robots in the real world. I think that's still an open question of like, how do we get from the lab into the real space? Many of the tasks, I think, were kind of curated in the lab itself. These are probably not tasks that are going to yet be deployed in the real world by necessity, so we need to think a little bit about that. I think primarily our work has been focusing on the generalization axis. I think we can see how broad can we go. But I think there's still the open question of, at some point you need to be hitting some level of performance that becomes viable in whatever settings you sort of care about. And that's still the open question here. So those are I think some of the limitations of what you're experiencing right now. Hopefully one day I'll come back and have a different presentation, which is kind of more advanced on that axis. But I think those are some of the things that we're still trying to push towards at the moment.
Yeah, so in the beginning you were mentioning whole body control, but the videos mostly showed that the base was relatively inactive. Like, did you also run tests on actual whole body control tasks, or was it mostly for the humanoids that the base was just fixed in front of the table?
For this work, the base was fixed primarily. It's very much an open research area for us as well to think about more dexterous and more complicated embodiments and more whole body control. So not in this particular work, but it's definitely an active field of research for many of us.
Thank you.
The last question, like more open question. So do you think in the future we are going towards a point where we have a mega VLA that is doing anything like navigation, manipulation, whole body control, etc.? Or we have these super good VLAs that, for example, in this manipulation task, I think at some point they will be excellent. And so I can see a lot of application in the industry, in other things. But they will be something that you activate at some point. And then the robot is actually controlled with other system. But then at some point you need this particular skill that is very complicated and to generalize to the situation. Then you activate the VLA. Like, how do you see? Like a VLA that is doing everything, or like that is just used at some point?
Good question. Honestly, I think what we've started to see is that there's definitely gains to be had when you're able to have this sort of multi-embodiment, multi-control setup. There seems to be, and I think we've seen some of that from maybe the vision and the language space, where there is something that seems to happen as you scale. It's not clear what that is, but there definitely seems to be something that's happening in a way that's harder to imagine. That being said, I can also see a world where there's limitations on what you can control all at once. So whether or not we end up with a single monolithic VLA that covers every possible robotic use case and form factor, I think that would, for us, is an area that we would like to see how far we can push that thesis. But then on the practical side, if there are limitations there, and if you have to have more specific modules, as it were, as part of a more cohesive and overarching system, I think that will be a very interesting tipping point. I think for us, trying to see what the frontier is as part of a sort of a single VLA backbone at the very least is something I think is kind of, we're very curious to see how we can scale that and what emerges from those properties, or if it hits, as you say, a limitation that has to be exploited elsewhere.
So thank you so much, Adil.
Have a great day, everyone.